All right, good morning, everybody. Welcome back to UAI Day 3 of the main conference. Hope you enjoyed the banquet last night, those of you who were there. Happy to start off Day 3 with another keynote talk, our last keynote talk of the conference. Today we have Lester Mackey, who's a senior principal researcher at Microsoft Research New England. Lester was previously taught in the statistics department at Stanford. His work on scalable machine learning has earned him a MacArthur Fellowship, as well as the 2025 COPS President's Award, which is one of the most highest honors in statistics, as well as many other accolades. His talk today is on compressing uncertainty in artificial intelligence, and we're very happy to have Lester here. Welcome.
Good morning, everybody, and thank you for coming out so early. Today I wanted to talk about compressing uncertainty in artificial intelligence, and in particular, how do we represent, compress, and propagate uncertainty efficiently. And the motivation for this talk comes from computational cardiology, where scientists are developing these digital twins of human hearts to non-invasively predict disease progression and therapy response. And this is necessarily a multi-scale sort of phenomenon because what happens at the single cell level in your heart also impacts the whole organ behavior. So for example, whole organ heartbeats are coordinated by calcium signaling in your cells. And it's known that dysregulation in calcium signaling can lead to these life-threatening heart arrhythmias. And so one whole line of work is around modeling the impact of calcium signaling dysregulation on your heartbeats. So let's think about that from an inferential standpoint. So we more or less know how calcium signaling works. We have models of this process in your body, but those models have unknown parameters. And so those parameters have to be fit to your data. So the first step is to estimate the unknown parameters in the calcium signaling model from your data. Okay, so now we've done estimation, and that means we have uncertainty, right? And so we're going to capture this uncertainty here by sampling many likely parameter configurations. And specifically, we're going to do this using Markov chain Monte Carlo. MCMC will eventually draw sample points from the posterior distribution, let's call that P, over your unknown parameters. Okay, and at this point, I want to highlight that this already might require millions of sample points just to adequately explore that posterior distribution. Okay, so this captures the uncertainty in your single-cell calcium signaling model. But what we care about is uncertainty around your heart. So we'd like to propagate that uncertainty through your whole heart model. And ideally, we'd do that by simulating the model for each of those sampled configurations. But this is where things really start to get expensive, because today, each heart simulation costs thousands of CPU hours. And doing that for millions of configurations is just prohibitive. So this raises the main question of this talk, which is, can we accurately summarize a distribution using many fewer sample points? And how do we do that? Okay, well, this is the question that underlies what I like to call distribution compression. That is, how do I succinctly summarize a distribution P using a small number of points? And likely you're all familiar with the most common solution to this problem. It's just IID sampling directly from P. Or if you can't directly sample, you might use a Markov chain that eventually converges to P. And why do we like these solutions? We like them because, well, first, they're readily available, and they're also eventually high quality, meaning that if I want to approximate intractable expectations under my target distribution, then I can do so with asymptotically exact sample estimates, which are just averages over the points in the chain that you sampled. It turns out, though, that there's also a drawback even to these very standard methods. And the drawback is that the samples are too large. So your typical integration error looks like n to the minus 1/2, which means that you already need about 10,000 points to get down to 1% relative error. And that quickly becomes prohibitive if you have a very expensive downstream task or function evaluation like heart simulation. But here's an idea. What if we still make use of these readily available high-quality samples and try to compress them? That is, we can reduce the problem of compressing a general distribution to one of compressing an empirical distribution. Okay, so how do you do that? How do you compress an empirical distribution? Well, you might reach for some of the same tools. You might go for uniform subsampling from the set, or IID subsampling from PN. In MCMC, a common thing to do is what we'll call standard thinning, which is just pick every teeth point in your Markov chain. And the drawback of these approaches is that you, again, get this large loss in accuracy. Your error blows up by square root t, which means that if you want to do heavy compression, say from n points down to square root n, then your error is blowing all the way up to n to the minus 1/4, so you've lost a lot. And the natural question is, can we do better than this? And to start to answer that question, I think it helps to look at the minimax lower bounds for the problem. Now, it's known that, from Phillips and Tai, that any procedure that returns just square root n points to approximate a distribution must incur at least 1 over square root n error for some target distribution. So that's a lower bound. And another lower bound tells us that any procedure at all that's approximating your target distribution that's only based on n IID sample points, again, has to incur 1 over square root n error for some target. So both of these lower bounds are pointing to the same number, the same rate, 1 over square root n. And what I want to highlight is, well, 1 over square root n is the error of the full sample Pn, and it's much lower than what we get from doing standard thinning or IID sampling. We don't necessarily incur the n to the minus 1/4 blow up. And so the question is this achievable in practice? Can we actually produce a subsample that has that same quality as the lower bound? And that's what we're going to strive for in this talk. I'm going to share some practical compression strategies that match these lower bounds up to 1 or 2 log factors. Okay, all right, so here's our setup. We're going to be given a set of input points, x1 through xn. There'll be an r to the d, and we'll call their empirical distribution Pn. Now, I'm not going to make any assumption about the provenance of these points. They could be pre-generated by any algorithm, so they could be coming from IID sampling, they could come from MCMC, they could also be deterministic points that you chose using quadrature or a procedure like kernel herding. The main thing we want from these points is that together they provide a good approximation to your target, but potentially a bloated one with too many points. Okay, and so then we're also going to have a target output size that I'll call S, and throughout the talk you can think of S as about square root n if you want to do very heavy compression. All right, and our goal then is to return a core set, which is just a subset of my input points that has cardinality S. And I'll call the empirical distribution of that subset Q. And the property we want from Q is that it has better than IID integration error between Q and Pn. So we know that IID this is of size S, so IID would be 1 over square root S. So we want to be able to do better than that. We want essentially little o of 1 over square root S error. Okay. So how are we going to measure the quality of these core sets? Well, I said that their goal is to return a core set with better than IID integration error between the input and the core set. And to do that, we're going to quantify error in 2 ways. The first is using what's called a maximum mean discrepancy, or MMD for short. And an MMD is literally the maximum discrepancy between input and core set expectations over a class of real-valued test functions. In this case, it's parameterized by a reproducing kernel. A kernel is a function of 2 arguments, symmetric in those 2 arguments, also positive definite, meaning that if I form the matrix of pairwise evaluations of that kernel, it's always a positive semi-definite matrix. Here are a couple of examples. There's a Gaussian kernel, looks just like a Gaussian density, except applied to x minus y. And the inverse multi-quadric, which is kind of like the Gaussian kernel, but it has polynomial decay instead of exponential decay. Okay, so that's our first quality measure. We're also going to use a finer grained measure of quality that I call the kernel sub-Gaussian constant, sigma. And I've given you the formula here, but the main thing you should take away from this is that if you have sigma sub-Gaussian, that means each of your core set expectations concentrates well around the input expectation with variance that's controlled by sigma. Okay. So now we can jump into the first algorithm. This is called kernel thinning. It has 2 stages, an initialization stage and a refinement stage. The initialization stage is called KT split. This is how it works. You're going to partition your input points into candidate core sets, each of size S. Okay, and each of these candidate core sets you can view as being derived by iteratively splitting your data set in half. So you take all your points, you line them up, you pair them up, and from each pair you pick 1 point. All right, so you pick one, you throw one away. Now you have half as many points, you pair them up again, and for each pair you pick 1 point, and so on until you get down to your target size S. And each of these intermediate steps is something we call kernel halving. In kernel halving, the goal is to take your input and to split it into 2 balanced core sets, S and S primed. By balance, I mean that the core set kernel mean is about approximately the same on both sides. Or equivalently, each core set kernel mean is close to the input kernel mean. Or again, equivalently, like that kernel sub-Gaussian constant sigma that I mentioned is small. So to give you some sense for this problem, if you just uniformly picked your set, if I just picked half the points uniformly at random, then that sigma constant would grow like 1 over square root n. And this is actually the source of the bloatedness and the slowness of the error decay in uniform sampling. So we want a smaller value than this, and to get a smaller value, we're going to use non-uniform randomness. In particular, we developed this Hilbert space generalization of a beautiful algorithm due to Alewies, Liu, and Sani called the self-balancing walk. All right, so this is how it works. You start with 2 empty core sets, S and S primed, and you're going to consider your input 1 pair at a time. And from each pair, you're going to select 1 point to enter into S and 1 point to place into S prime. How do you do that? Well, first you just try adding X to S, and you try adding X prime to S primed, and you compute a measure of the balance, the difference between those kernel means. And then you do the opposite. You try adding it to X to S primed and X prime to S, and again you measure their balance. And now you're going to flip a coin, and that coin is going to be biased toward the more balanced solution. And it turns out you can do this in just the right way so that your result maintains this sub-Gaussian constant, but the sub-Gaussian constant is now much smaller. Instead of being 1 over square root n, it's just this number, which looks like square root log n over n. And this is completely explicit, and there are a couple of interesting things to note about this. First, it doesn't depend on the dimension of the problem at all. Second, this is true for any kernel on any space. So we're working in R to the D, but if you have a kernel on graphs, some other more complex space, the same sort of guarantee holds for this algorithm. Okay, so that's one round of kernel halving, and now we need to chain this together over and over again so we can thin down to our target size S. And because of uncorrelatedness between each of these halving rounds, after S, when we get S points out, the sub-Gaussian constant is square root log S over S, which is great because that's much smaller than the 1 over square root S we'd get from uniform sampling. Okay, and it turns out you can also convert this into guarantees about MMD. So remember, we have these 2 different quality measures. MMD is a much larger quantity, but under various circumstances, you can convert your sub-Gaussian constant into an MMD bound. So for example, if your kernel features fast eigenvalue decay, the sort of decay you get from a Gaussian kernel or an inverse multi-quadratic kernel, then your MMD is just bounded by the sub-Gaussian constant sigma times some extra log factors that now depend on the intrinsic dimension of your data. More generally, if you have slower polynomial eigenvalue decay, you still get these faster than IID rates out from your MMD. Okay, great. So that's the first step. There's a second step to kernel thinning, which is a refinement step. So I said that we're actually dividing the core set into a bunch of different candidate core sets of size S. So in KT swap, the refinement step, the first thing you do is you pick the best of them. Pick the one that's closest to your input in terms of MMD. And then you iteratively refine that core set by taking each point, kicking it out, and replacing it with the best input point, the point that minimizes MMD the most. It turns out that both of these steps together are dominated by the need to evaluate these kernel evaluations at n squared points, at every pair of points, so that's n squared kernel evaluations. But you can reduce that runtime for heavy compression like we want. You can reduce that runtime to near linear using a meta-algorithm we've developed called compress++. And I won't say anything more about that algorithm for right now beyond that it speeds up thinning algorithms without ruining their quality. Okay, so let's see this in action so you get a feel for how kernel thinning works. On the top, I'm showing you IID samples from a mixture of Gaussians with 8 components. And on the bottom, I'm showing you kernel thinning samples of the same size. And what you notice is that for a small number of sample points, you're getting better stratification across your components, whereas the IID sample, just by chance, tends to miss some modes completely and oversample other modes. Because you're oversampling and then thinning, you hit each of your modes, and that's the highest priority. Then as you move to larger sample sizes, you see less clumping and fewer gaps relative to the uniform, the IID sample. And that's a picture, but you can also quantify this. You can also measure the MMD between your samples and the target Gaussian in this case. And here what you can see is that for mixtures of Gaussians with different number of components, kernel thinning is improving both the rate of decay. So instead of your n to the minus 1/4 rate, which is what you get for square root endpoints from IID, you get n to the minus 1/2. But it's also improving the order of magnitude of your MMD, even for a small number of points. Like even for 4 points here, you're still seeing an improvement in MMD. And for 8 points, it's a pretty big improvement in MMD. Now, I mentioned something about MMD. I said that because it's a much bigger measure, it can also depend on the intrinsic dimension of your data. And so you might wonder, does this still hold in higher dimensions? So this is a 2-dimensional problem. So we were interested in that too. And so here's a series of plots where the target is now an IID Gaussian in d dimensions, where d ranges from 2 to 100. All right, so the 2-dimensional plot looks like what we saw before. Here are some of the higher dimensional plots. And what do we see in dimension 100, for example? Well, we see that still, in dimension 100, we're still improving the rate of decay. And also at 8 points, we're still seeing an improvement. That is, even after selecting 8 points in 100 dimensions, we're still getting an order of magnitude improvement in our MMD. Okay, all of that was IID sampling, but this was all motivated by having complex posterior distributions that we want to approximate. So now let's talk about some posterior inference problems. So here, from now on, or in this next section, P is going to be the posterior distribution over the parameters of a coupled system of ordinary differential equation models. And there are a few different models we'll study. So the first is this Goodwin model of oscillatory enzymatic control. That's a 4-dimensional model. It has 4 parameters, unknown parameters. There's the Lotka-Volterra model of predator-prey evolution, again a 4-dimensional model. And finally, there's this Hinch model that I mentioned of cardiac calcium signaling. That's a 38-dimensional model, and that there are 38 unknowns. And remember here, our downstream goal is to propagate our uncertainty through this whole heart simulation, which means that every sample point we can discard using thinning can represent thousands of CPU hours saved in downstream simulation. Okay, so we need input points, and the input points here are going to come from MCMC. We're going to consider 4 different Markov chains, a Gaussian random walk, an adaptive random walk, a metropolis-adjusted Langevin algorithm, and a preconditioned Mala algorithm. And to give you an idea of the scale, for the cardiac model, running the Gaussian walk to generate a chain of about length 4 million took 2 weeks of CPU time. So the time that we spend compressing is going to be dwarfed in comparison to just the time of acquiring the sample. Okay. So here are some results that are similar to what we saw before in that I'm showing you the MMD. This is the MMD between your input Markov chain and your output core set. Every row in this chart represents a different model, and every column represents a different Markov chain. So in the first 2 columns, we have the Goodwin and Lotka-Volterra models, and there the results are similar to what you saw before. So you're seeing improved rates of decay from kernel thinning. Standard thinning, which is just taking every teeth point of your chain, gives you this slow convergence. And we're getting much faster convergence using kernel thinning instead, so that's great. And in addition, we get improvements in the actual MMD, not just the rate. In the third row, I'm showing you the Hinch model. This is the cardiac model. And something interesting happens here. Standard thinning itself is actually doing much better. It's actually giving you a faster rate than you might expect. And there are reasons for that, and we can talk about that. But even there, kernel thinning is still improving the rate of decay and the actual magnitude of the MMD. So for example, here you can match the same MMD with half as many sample points, which means half as many of those expensive evaluations that you need to do, expensive simulations. Okay, so it seems like we solved the problem. We still have lots of time left. We could all go home early. But actually something's wrong here, and there's something wrong that you can't actually read off from these sorts of charts. And that something that went wrong is, in the Hinch model, the Markov chains haven't actually mixed. Now this wasn't true in the Goodwin and Laca-Volterra models, but it is true in this Hinch model. And how do I know that? Well, our collaborators provided two different Markov chains from different starting points. And of course, because they're meant to approximate the same distributions, so they should be overlapping one another, right? And so it's a 38-dimensional distribution, but I can project those distributions onto their marginals for different parameters. And if I plotted their marginal distributions in green and red, you'd expect they would look the same because they're approximating the same distribution. But in fact, what you see here is that often they're not even overlapping one another. They look very different from one another. That's a classic sign that your chains haven't mixed yet. And that's bad. That means they're not yet giving you a good approximation for the target distribution P, that posterior that we care about. So what are we going to do? A common thing to do is to use a more diffuse, tempered posterior. We'll call that P tilde, that allows for faster mixing. And that's a great idea. That's something we're going to do. But it also introduces a new problem. It introduces a persistent bias into our problem, because now if we have a Markov chain approximating P tilde, it's no longer approximating P. And so our sample is summarizing the wrong distribution. And so this raises another interesting question for us, which is, if we're already doing this compression, can we correct for those biases while we compress? And these sorts of biases arise in lots of places when we're doing posterior inference in particular. So there are a variety of different biases due to off-target sampling. Tempering is one of them. Another is approximate Markov chain Monte Carlo, which has gotten more popular, where instead of running the exact Markov chain that leaves your target invariant, you make an approximation that's just more computationally efficient or convenient to run, and then you're left with a target that's not exactly approximating. You're left with a sample that's not exactly approximating your target. Another common case is what's called burn-in. That is, whenever you run a Markov chain, you have to start it somewhere. In this case, the Markov chain, we started somewhere up here, which is outside of the high-density region of your target. And so the Markov chain has to find its way to the high-density region, and once it's there, then it happily samples around, in the space where we care about sampling. But we're left with this tail of points that really have nothing to do with the target. They just have to do with your starting point. That's another source of bias from which is often called the burn-in bias. So we'd like to be able to deal with these biases, but the problem is that we can't rely on the sample alone to deal with these biases because the sample is no longer targeting P. Somehow we need to measure quality directly to P to correct for these problems. So let's revisit our quality measure. Before we were measuring this MMD between Pn and Q, and I'm saying that now that's insufficient because Pm has these biases, I don't know what the biases are. So what I'd like to do is measure the MMD directly between P and Q. And to help us do that better, I'm going to rewrite the MMD in a special closed form. So here's a closed form version of the MMD, which tells us that all the MMD is doing is just computing integrals of your kernel under your target P and your core set Q. But this also highlights a problem with MMD, which is that, well, to compute it, we have to integrate under P, but integration under P is exactly what we don't know how to do. The whole reason why we're even sampling and trying to approximate P is because we don't know how to integrate under P. So this is a problem. It tells us that actually most MMDs can't be computed directly to P because we can't compute the expectation of the kernel. But what if we only considered a kernel, a special kernel, that we knew a priori was mean zero under the target P? Well, that would be a beautiful thing, because then all of these integrals under P would go away. We'd only be left with expectations under Q, which are easy. Those are just averages. Those are just sample averages. We can do that. And so then we would have an MMD that was actually computable. Well, it turns out this is exactly the idea that underlies what's called a kernel-Stein discrepancy. A kernel-Stein discrepancy is just a special MMD with a special kernel that you know a priori is mean zero under your target. And I'm going to show you the form of the most common kernel-Stein discrepancy kernel. It looks like this. Oh, okay. The details don't matter so much. There are two things I want you to take away about this expression. First, that this kernel is indeed mean zero under P under some mild conditions. Specifically, if your score function is integrable, then it will be mean zero. So that's great. And the other is that it only depends on P through the score function, through the gradient of its log density, which means that this is still potentially computable even if you don't know the normalization constant of your target, which is a common case if you're doing probabilistic inference. Okay, so that's great. So now we have something that we can compute. We have an MMD that we actually could compute, and that lets us measure quality directly to P. But then you might say, Lester, you just made this thing up on this slide. I've never heard of this before. Why should I use this quality measure? What are its properties? How does it relate to anything that I do know? And we've had similar questions about this, and we've been exploring, for example, when does controlling MMD also control convergence and distribution? Because that means that all of your bounded and continuous function expectations are converging, which is a nice property to have, and that we have for other standard MMDs. So there are a variety of results of this form. I'll give you just one example. So this says that, well, first of all, the kernel-Stein discrepancy depends on a base kernel that you get to choose. So let's say that you chose the inverse multi-quadrant kernel that we mentioned earlier as your base kernel. Then, if your target has a Lipschitz score function and strongly log concave tails, so it doesn't have to be a strongly log concave distribution. It can do somewhat arbitrary things in the center of the distribution. It could even be a mixture, like a mixture of Gaussians, but it has strongly log concave tails. Then minimizing the MMD, also sending the MMD to zero, also means that your sample is converging to P. That is, the KSD controls convergence and distribution. All right, and it's nice to have results like that, and this sort of proof provides template for other classes of distributions as well. Okay, so what are we going to do with this kernel-Stein discrepancy, this special MMD? We're going to do something that we call Stein kernel thinning, which is our solution for compression with bias correction. It has two steps. The first step is a bias correction step, and the second step is a compression step. So how do we do the bias correction? Well, what we're going to do is we have this input point set, this Markov chain, that has some bias. It could be targeting the wrong distribution. It might have burn-in. So what we're going to do is we're going to minimize the KSD using points from that input set. So first, we're just going to pick the single point from the input set that gives the best approximation in terms of KSD, and we're going to add that to our approximation Pn, or P1 so far. And then we're going to iteratively build up this debiased empirical distribution, each time by adding in the single point that leads to the best improvement in MMD when you average it in. This means in particular, and we're going to do this over n steps, so we're starting with n points, but we're also going to end with n points. And this means in particular that the same point can be chosen more than once. And the total runtime after n steps is n squared, similar to what we saw for kernel thinning. Okay, so now we have this debiased Pn, this debiased empirical measure, and now we want to compress it. And to do that, we're just going to fall back on what we learned earlier. We're going to take Pn, we're going to use kernel thinning, and we're going to compress it to a core set of a much smaller size, for example, square root n. Okay, so what can we say about this algorithm, the Stein kernel thinning algorithm? Well, here's a representative guarantee. It says that the MMD, now we can measure the MMD directly to P, right, which is great. And this is giving us a quality guarantee for how close you are to P. And it has two terms in it. The second term is the same sort of compression error that we saw before. It's this basically 1 over S compression error that we saw earlier. But the first term is something more interesting. It says that Stein kernel thinning performs nearly as well as the best simplex reweighted version of your input point set. So before, all we could do is say that, well, the unweighted input point set is a good approximation, so I can just approximate that and life is good. That's not sufficient anymore because the input point set gives a bad approximation, but it's possible that a simplex reweighted version would give a good approximation, and we want to compete with that. So why is that useful? Well, for example, it says that Stein kernel thinning performs as well as your input sample after you've removed all the burn-in. Because you can always give a weight of 0 to all of these burn-in points, and then give equal weight to all these other points, and that's in your competitor set now. So that's good. It also means that you can perform as well as an off-target sample after doing optimal importance sampling reweighting. And this is because self-normalized importance sampling also falls into the class of simplex reweightings. And in this case, you don't need to compute the simplex, you don't need to compute the importance sampling weights, you don't even need to know what the proposal distribution was. So we can formalize that a bit. Here's a theorem. It says that imagine you drew your input points IID from the wrong distribution p tilde, and then you handed it off the Stein kernel thinning and you said, give me a good core set approximation. Then this says that the core set approximation converges to the target distribution like 1 over square root n, assuming that you used square root n points, a heavy compression setting, even though you sampled from the wrong distribution. And the same result extends to geometrically ergodic Markov chains. Okay, so what can we do with this? Let's see Stein kernel thinning in action. So first, let's see how this works when you're trying to correct for burn-in. I mentioned that one of our targets is this Goodwin model of oscillatory enzymatic control, and I'm showing you a 2D projection of a Markov chain that we ran. So we started our Markov chain over here, and it spent a long time trying to find its way to the posterior distribution, which is all inside of this little box. In fact, about half of the points were spent just getting to that box, and the other half were spent happily sampling in the right regime. So how do you deal with that when you want to do inference? A common way is to run many different Markov chains. You could couple them, you could use them to get an idea for within versus across chain variance. There are a number of different diagnostics you could use. Here we've used one of them, a 6-chain diagnostic, to determine that burn-in happens around here, so then we throw away all the red points, and then for the points that remain, we use standard thinning to just pick every teeth point to retain. And that gives us the yellow points in this box. Alternatively, what you could do is just take your single chain and hand it off to Stein kernel thinning and say, give me a good core set. And it ends up not picking any of these red points because none of those red points help it approximate the target. None of them help it minimize that KSD. Instead, it picks these yellow points, which looks similar to what you would have gotten using this more elaborate multi-chain diagnostic. Okay, and so you can also quantify the quality of these chains, and that's what I'm doing on this slide. So in green, I'm showing you the quality of Stein kernel thinning, and in blue, I'm showing you the quality of burn-in removal with standard thinning. And what you can see on the top is that, well, Stein kernel thinning is offering you a better MMD, this better KSD that it's actually optimizing for, which is good. And on the bottom, I'm showing you a second metric, which is called the energy distance, which is not being directly optimized for, just to show you that these improvements translate to other metrics as well. Okay, that was burn-in removal, but again, our motivation was tempering, right? We're trying to solve this cardiac problem, and there we're using a tempered distribution to get faster mixing. And I mentioned before that the issue was, when I just ran Markov chains targeting my target directly, the chains weren't mixing, their marginals didn't overlap. That was a telltale sign that I had poor mixing. The point of this slide is just to tell you that when I instead run my tempered chains, the mixing is much better. The marginals are much closer to one another, so that's a good sign. So now we've run samples targeting the tempered distribution, and I want to use those to do inference. So let's consider a few different ways to do inference here. The first thing you might do is just run your Markov chain to approximate the tempered distribution, and then just use it. I can't use all the points because there are too many, right? So I could just use standard thinning to pick out every teeth point, and then run that and use that to approximate my posterior. If you do that, you get this curve in red, which shows some improvement in the beginning, but eventually it bottoms out at a point that's very far from the target. And why is that? It's because you're summarizing the wrong distribution. So you're never going to get a good approximation because no matter how good your subsample is, you're still summarizing the wrong distribution. Oh, sorry. That's the blue curve. The blue curve is summarizing the wrong distribution. If you used the original points, you could say, okay, let's just use my original points. I said they didn't mix well, but whatever, let's just use it. You could do that too. That actually gives you a slightly better approximation. You don't have the bias aspect, but you still don't get a good approximation because you haven't fully mixed. So again, you're still essentially summarizing the wrong distribution. You haven't gotten all the way there. You're summarizing some intermediate distribution between your starting point and your target. Okay, finally, what you could do is you could take your tempered chain and pass it to Stein kernel thinning and say, give me back a core set that approximates P well. And when you do that, you get this much better approximation in green here. Okay, so let's summarize what we've talked about so far. I introduced these new tools for summarizing a probability distribution more effectively than IID sampling and standard Markov chain Monte Carlo thinning. There was kernel thinning that compresses this endpoint summary into a square root endpoint summary with better than IID approximation error. There's Stein kernel thinning, which simultaneously lets you compress and correct for biases. And these biases could come from burn-in or approximate MCMC or tempering. And then I hinted at this algorithm that I called compress plus plus that I told you speeds up thinning algorithms without ruining their quality, but I didn't give you any more detail. And so I think it's worth giving you a little bit of detail so you can understand how that works. So how do we do this? How do we take one's favorite thinning algorithm and turn it into a faster one that doesn't ruin its quality? Well, the way we do this with compress plus plus is instead of applying, say, a halving algorithm to the full point set, which is expensive and takes n squared time, we're going to orchestrate a series of smaller halving problems. So we're going to divide your point set up into bins of size 4, and then we're going to have each of those bins. And then we'll collect all the results. And then we're going to divide it up into bins of size 8, and we're going to have each of those bins and collect the results. And we're going to keep doing this. Each time your bin size is going to get progressively larger, so in a geometric way. It turns out if you do this, you can reduce n squared time down to near linear time, n log cubed n. If you do this and you have a target output size that's small, like we're doing heavy compression, so say s is equal to square root n, the biggest halving problem you ever encounter is now it's of size 2s. So that's of size 2 square root n. And so now if your quadratic time algorithm turns into a linear time algorithm because you're only ever applying it to small subsets. But you can also do this in a way where you can apply it to any halving algorithm. So even if it has no guarantees about quality, but you like it, you can still pass it through compress. And it will never inflate its error by more than a factor of 4, even if you don't know what that error is ahead of time. And so these charts are meant to show you that sort of thing in action for kernel thinning. So in green are the green curves are kernel thinning. The blue curves are this compress plus plus. On the top, what you see is that the quality is about the same. Green and blue are close to on top of one another. These are the same sorts of plots that we saw earlier for the Gaussian target in d dimensions. But meanwhile, on the bottom, we see that the speed is a lot better. So here I'm showing you just single core runtimes. And with a single core, it would take a day of computation to run your kernel thinning algorithm, and dimension d equals 100 on an input size of 10 to the 5. But it goes down to 1 hour using compress plus plus with no significant loss in quality. Okay, so this is great because on top of what we've talked about so far, this unlocks a number of applications in statistics and machine learning. So one relates to two-sample testing. This is when you want to test whether the quality of my generative model, for example, matches the quality of my ground truth data. A common way to do this is with an MMD test, which is non-parametric. They're high-powered tests, but they're also very expensive. Just computing that MMD, again, requires quadratic time in your sample size. But what you could do instead is run a compression algorithm, like kernel thinning with compress plus plus. You can compress each of your samples, measure the MMD between the compressed samples, and because of the quality guarantees that I've discussed so far, you can do that without any significant loss in power. And that's what I'm showing you here. Each of these curves is a power versus runtime curve. And This top right point here is the power that you get from just running your exact test, running the standard MMD test. And this red curve is what you get from running compressed plus kernel thinning with different levels of approximation quality. In particular, for the highest level of approximation quality, you get the same power, but you do it in 10 seconds instead of 5,000 seconds. And there are other algorithms that are meant to trade off between quality and power, but the trade-off is much worse in terms of runtime. So power gets lost much more quickly, and so you don't gain as much in terms of runtime. Okay, another application is to actually training your models. So say, training your favorite neural network using stochastic gradient descent. There's this beautiful idea, originally due to Harvey and Samadi, and then extended by Cooper et al. In this algorithm called CD-grab, which says that if you have a good algorithm for balancing, that is for like taking your input and splitting into two halves such that the two halves are balanced, then you also have a good algorithm for reordering. You could use any balancing algorithm to reorder your stochastic gradients in a way where the cumulative average of stochastic gradients is closer to the overall mean than you would get from just uniformly sampling. And what this means is that you can actually make training with stochastic gradient descent much faster. So here I'm showing you in green the training and test accuracy curves from uniformly sampled SGD. You just pick a uniform order each time. And in blue, I'm showing what you get when you use kernel halving SGD to do that reordering instead. And what you see is your training curve decreases much more rapidly, and your test error also increases more rapidly when you use this kernel halving SGD. Okay, and here's a third application. This is to attention. So if I were to give a one-sentence summary of this, it would be that you can use compressed kernel halving to accelerate attention by approximating it in a way that is both cheaper and accurate. But I think we have a little bit more time, so I can give you more than a one-sentence summary. And to do that, I think I should back up a little bit and just tell you what I'm talking about here. So this application is motivated by transformers, the neural networks that revolutionize the way that we do natural language processing and vision and even speech processing over the last decade. And what's interesting here is that at the heart of the transformer is this module that is simultaneously very effective and very expensive. It's called the attention mechanism, and this is how it works. So inside of attention, you're taking in an input sequence. Here it's a sequence of n queries, keys, and values, each of which is represented by a vector in r to the d. And given these queries, keys, and values, you first want to compute the similarity between each query and each key, and then you compute a weighted average of the values that's weighted by those similarities. Now, the reason why we do this is because it's had unprecedented success in capturing the long and short-range dependencies amongst elements in your sequence. But it also has a pretty big drawback, which is that it's very expensive to compute. And it's expensive in two different ways. So first, there's a time expense. Because I have to compute this big similarity matrix, that takes n squared time. And that means that if you have a long user input to your language model, say, it takes a long time to process and consumes a lot of energy. And also, if you have a long model generation from, say, your reasoning model, that also takes too long to produce and, again, consumes a lot of energy. Okay, so that's one cost, but there's also a second cost, which is a memory cost. Your memory cost actually grows linearly with your sequence length, and this is because you need to keep around the keys and values from prior tokens so that you can attend over them in the future. So every token that you process gets stored in what's called a KB cache, and that cache grows linearly with your sequence length. And this puts a hard limit on both the maximum context length of your models and on the maximum generations that these models can produce. Okay, so these are the costs. And a question which I think falls into the scope of our talk today is, can we approximate this process both cheaply and accurately? And you might wonder, like, why would we even hope to to approximate it well? Well, it turns out that attention at the end of the day is really just averaging. Let's zoom in on a single entry of the attention output, the ijth entry. Every entry of the attention output is just a ratio of two averages. On the bottom, it's the average of those similarities between a single query and every key. And on the top, it's a weighted average of the values weighted by those same similarities. And averages are exactly what we know how to approximate now, right? This is what we've been doing this whole time. We've been approximating averages. And so particularly you might think, well, what if we just picked a subset? Let's pick a subset of our tokens, S, and approximate those averages just using that subset. Now, if we only have S tokens now instead of N, then we get some immediate benefits, right? Our runtime is now only NS for attention instead of N squared, so that's great. And then also our cache size goes down. We only have to store S tokens instead of N tokens, so our memory cost decreases. So then, okay, that's great. So that all seems perfect. But then how do we pick this subset? The first thing you might think of is, well, let's just pick a uniform subset of the entries. And if you do that, then you'll get that typical IID error, right? You'll get that 1 over square root S error, which is something, but you might hope that you can do better. You still here would need 10,000 tokens to get down to 1% relative error, which is more than you'd like, or it's not offering the best trade-off. And so the question is, as usual, can we do better than this? Well, the answer is yes. We can do better. And one way to do better is to apply what we've learned so far in this talk, which is let's just apply this compressed kernel halving algorithm to this attention problem. And in particular, we're going to use a special kernel, and that kernel is motivated by the form of the attention mechanism itself. So it's an attention kernel. It's a product of an exponential kernel for the keys and a linear kernel for the values. And so the solution, which is compressed kernel halving for this attention kernel, we call it thin-former. And what does it do? It outputs S tokens that has subset averages that nearly match the full averages over your full sequence. And you can also bootstrap that into a guarantee for the attention output. Roughly, this guarantee looks like the following. It says that all of my attention averages are bounded by something that looks like log S over S again. Okay, and it turns out you can do this in S squared time, which is an amount of time that's actually going to be dominated by the time to attend. So the overhead from doing the compression is actually small compared to what you're going to do with the core set thereafter. Okay, now as I've described this is a solution for the unmasked attention problem. But often when you're doing language modeling, you want to do what's called masked attention, or causal masking, which means that you only attend over the tokens you've seen in the past rather than attending over all tokens. So to boost thin-former into a causal masking solution, we've created an algorithm called Express. Express takes in an unmasked approximation and outputs a masked approximation without ruining its quality. So in this case, the application to thin-former, which we call thin-former Express, supports causal masking. It allows you to do online generation, and it maintains a core set of size S in S squared log squared n time. And it guarantees that you have about 1 over S masked attention error for every query. And on the right here, I'm showing you both the nature of masking, so we're only ever attending to the left instead of attending over all tokens. And this is showing you a typical rollout of Express in terms of the core sets that are being picked. Okay, so what do you do with this? What do you do with an algorithm like this? Well, the first thing you might think to do is let's try to speed up long context processing. Speed up the processing of the long inputs that a user gives to a language model. This is called prefill. And here, I'm comparing thin-former with varying levels of quality. So this is like with a varying core set size. You'll see this parameter h floating around. H represents 2 to the h is the core set size s. So I'm comparing thin-former on the left, runtime, to a standard approach to exact attention called flash attention. It's very popular. It's very efficient. It's I/O aware, so it takes into account different levels of caches, so you're not wasting a lot of time moving data around. And I'm showing you here speed up over flash attention too. And as you see, as the sequence length grows, the speed up grows. And this is what you should expect, because standard attention runs in quadratic time. Here I have a fixed core set size, so it's essentially running in linear time, so your speedup gets better as your sequence length gets longer. I'm also comparing with another algorithm called hyperattention that's designed to approximate attention. It does a few different things. First, it looks for the largest entries in the attention matrix and quickly identifies them and removes them. And then it uses uniform sampling to approximate the remaining keys and values. And what you see here is that we're getting bigger speedups on the left, but also a better trade-off between runtime and quality on the right. So here the quality measure is relative perplexity. In this case, all the models are doing rather well in that the relative perplexity never gets very high, 1.06 relative to the exact. But you can see that we get a better trade-off between quality and runtime from these thin-former approaches. OK, after you approximate prefill, you want to do generation. But you still need to enter all of your tokens into this cache. And so you get hit with this memory cost that I mentioned earlier. And so there are a variety of solutions that try to reduce that memory cost. Those are called KV cache compression procedures. So I've shown you three of the more popular ones here: streaming LLM, snap KV, pyramid KV. Each one effectively reduces memory. But each of them also has to wait for prefill to be processed first. So they still incur this long runtime before they can apply their compression techniques. So one thing you could do is instead apply thin-former express, use that to accelerate prefill. It then hands the tokens off to your favorite KV cache compressor. And what I'm showing you here is that results in basically the same level of quality, but in less time. So the green curves are what you get when you use express. The gray is what you get when you use exact attention. You get the same level of quality in less time. Lastly, I want to mention that you can also do generation with these tools. And there you, again, run into the same two problems. One is every token you generate has to be placed into your cache, or you end up with this linear memory cost again. In that case, you can use thin-former express to control your budget. You can say, I never want more than S tokens in my cache, and then see what's lost in terms of quality. And so here I'm showing you trade-off curves for thin-former express, plus a variety of other techniques that are already out there for doing this sort of budgeted reasoning. And what you see is that we're getting a better trade-off between quality and cache size. And also, we can match exact attention quality using 61% of the cache size. So that's great. And the story is similar for runtime. If I use thin-former express to trade off runtime versus quality, again, we're getting a better trade-off than the other tools that are out there. And you can match exact with about half of the runtime. OK, we're running low on time, so I'll just say that one thing we didn't really talk much about is the fact that I'm using an unweighted approximation. It turns out that you can't do much better than what I've described. You can't really do better than 1 over S if you, in the worst case, if you're using an unweighted approximation. But you can do better if you use weights. And we have a solution now for that problem that's called Wildcat. You can get this, in fact, much faster rate of decay when you're doing heavy compression, something that's super polynomial, so like 1 over n raised to a power that itself depends on n, that grows with n. And in practice, this leads to even better approximation errors. So as your sample size grows, your speed up improves, but also your error improves, which is great. All right, and so here's some examples with KV cache compression. I'll skip over that so we can jump to the end. You guys can ask your questions. So to conclude, I've shown you now a variety of applications to two-sample testing, to SGD, to attention with thin-former and Wildcat. I think we really just scratched the surface here, and I think there's a lot more to do, and I'd be happy to talk with any of you more about that. So thank you for your time.
Thanks very much, Lester. We have time for questions. Raise your hand. There's some volunteers with mics walking around. I think there's one right here.
Yeah, thank you. Great talk. I was wondering, if I understood this correctly, all you did is agnostic of the F, which you're trying to integrate, and which makes sense for your application, because F is this horrible simulation. But if you have some more information about the F, can you use this somehow to make this more effective?
For sure. So I mean, if you knew the F exactly, that would be the best case, and you'd work more directly with it. Although often the problem with F is that you don't want to evaluate it, at many points. In some sense, the information about the F is baked into your kernel choice. So these guarantees are not for an arbitrary F; they are for F belonging to that RKHS, and then have controlled norm in that RKHS. And so you'd want to bake in the knowledge you have about F into that choice of kernel.
Okay. Yeah. I see. Thanks.
Other questions? Yeah, right here.
Okay, so thanks. That was very inspiring. I was wondering about the first part of your talk. You always first did the MCMC, so then you got a big sample, and then in the second stage you sampled from that big sample. Is there some way to do it online, like on the MCMC on the fly thing? I don't know.
Yeah, so we do have some tools for doing that sort of thing. One is called Stein points, and it again uses this kernel Stein discrepancy, but it uses it to pick the points that you want to add to your set directly. And there's some difficulties there. Well, the biggest difficulty is that you have to, essentially choose a point from any candidate in your entire space, so then all of R to the D. So we have something that's a more hybrid, but closer to the online state you're mentioning. It's called Stein point MCMC, which is at every step, instead of considering all possible points as the next point to add, you run a short Markov chain from your current point, and you use those as the candidates for the next point that you're going to pick. And you pick the next point by minimizing your KSD, and then you iterate. So at every step, you generate candidates with MCMC, and then you pick a point, and then you move on. And that's something that's more of a hybrid solution that we find to be more practical. Yeah.
Okay, thank you.
Yeah.
Other questions?
Hi. Hey, great talk, thanks. I was wondering about this time-saving motivation that you gave, because in your application you already had the Markov chain, right? So, and then you compressed it, but if you already have generated a chain, then how does it save time?
Great question, great question. So this Markov chain is meant to summarize the uncertainty around your calcium signaling model, which is just one small component of the heart model. And once you have all that uncertainty, these are like different parameters for that model, then you want to simulate your heart model for every one of those parameter configurations. So that's the really huge cost. Like, it did take us 2 weeks to sample the chain, or 2 weeks of CPU time, but every simulation itself costs another 1,000 CPU hours. So the biggest expense is the simulation. And so what you're trying to do is you get your chain, summarize it to a smaller number of points, say maybe like 1,000 points instead of 4 million, and then only run your expensive simulation on that smaller number of points.
More questions? I actually have a quick question. I was wondering if you could say something about how, so if you talked about how the sampling technique can correct for a certain kind of problem with your MCMC, but another kind of problem you might have with the original MCMC sample in the first place is like some sort of non-identifiability or like label switching, or it's not, the parameters themselves are not well separated enough so that it's doing a bad job of sampling the space. Do you know the consequences of your thinning method for anything like that?
Well, I guess it depends on the nature of the error. So the nice thing is that it's just going to provide, since it can measure quality directly to P, it's just going to try to find the best approximation to P given whatever you've given it. If your problem is that you just haven't sampled some of the modes, then there might be no way to correct for that if you only give me samples from the other modes, but it will still give you the best approximation it can given those points. And in particular, it gives you an approximation that's close to the best simplex reweighting of your points. So you can think about it that way. If there is a good simplex reweighting of my points, then this approximation will be good. Otherwise, it's still constrained by that limit.
I see. Okay, thanks. I think, yeah.
Hi, thanks for the great talk. So I had a clarification question about I think it was KHSGD, where you were talking about the CD grab. And so the question is that from my understanding, CD grab has this problem searching for the right permutation. So is what you're doing is that you make that search more efficient?
Yeah, so there's this nice reduction due to Harvey and Samadhi that says if you can split an input point set into half and split into 2 core sets, then you can use that halving to reorder the points in a specific way. There's just a deterministic map. So what you do is essentially I just run kernel halving on the input, and then I use the map to reorder, and then on every iteration you do that again, and the ordering gets better and better as you go through the algorithm. So essentially, you find the permutation by doing the halving.
Thanks.
Yeah.
We have time for maybe one more question. No? If not, then let's thank our speaker again. Thank you, Lester.